Last week we started this chapter 8, on factors and factoring, and we specifically looked at the first 4, although we didn't finish the last one. And there was one example in 8.3 that I would like to revisit as a way of, I guess, looking at 8.5. So, let me know if you have any questions as we go through these slides. But let me go back to the question within section 8.4, the one that we actually stopped at. It was this question here. X squared minus y squared plus 2x plus 1. And the idea was to factor the expression. And I guess one hint is it's part of this section, but going forward, remember, when it comes to a factoring expressions, you wouldn't have hints like this. You'd have to try to figure out what technique you could apply. And the first and foremost technique you could always try to see if it works is common factoring. And then there are other techniques like difference of squares, quadratic, trinomials, grouping, and so on. Okay. Now, let's say we didn't have this specific heading in here. Let's say the question was just to factor the expression. Again, try common factoring. Is there anything in common between these 4 terms? You're right, nothing at all. Which means common factoring cannot work. Difference of squares wouldn't work because difference of squares needs you to have 2 terms. Or if you could express these 4 terms as somehow a difference of 2 squares, then maybe you could do it. This is not a quadratic trinomial situation because it has 4 terms, and so grouping is something you could try. How many of you finished this question already, by the way, this example? You got the right answer? Oh, okay. Did you get, well, what did you get?
X plus y, x minus y, and then 2 bracket x plus y.
Ah, okay. And there's a plus or minus sign between them? Okay, all right. So unfortunately that answer is wrong. But we'll go into why that is the case. Did anyone else try it? And you got the answer? Well, what did you get?
X plus 1 plus brackets, and another one brackets x plus 1 minus.
So let me write that out. You said in one bracket x plus 1?
Yeah.
And then another bracket x.
Plus.
Sorry. Plus.
X plus 1 plus. Oh my god, how do you say that in English?
Oh, the y?
Yeah.
Okay. And second bracket?
X plus 1 minus.
Okay, all right. I believe this is the right answer. Did anyone else get this answer? By any chance? No? Okay, all right. We'll see why this is the answer and why the others aren't. So let me first of all try this out using something you may have already tried to get something that you may have possibly, let's say, reach a step that you may have, or stage you may have reached. Now, what we talked about with grouping is, in the beginning, you can try grouping 2 terms at a time. And if you try this out, one way of trying it out, I'm not saying this is the right way, but let's say we had nothing else to go on, you could try grouping these 2, and let's say you could try grouping these 2. Why not? Is there some kind of factoring you could do here? Common factoring? No, because there's nothing in common between them. But you might say, okay, you could write that as a difference of squares. So you could do that. And between the the third and the fourth, there's nothing really you can take out common or do any kind of factoring with those 2. So even though we did some kind of factoring here to get these 2, this resulting expression over here, do you think that expression is in factored form? Why not? Sorry, say that again? Well, but why? What would be the answer? the thing about factored form, and you can take a look at all the other answers we've ever had, factored form would always have a product at the end. Like you'll have, let's say, this is one factor, this whole thing here is one factor, and this is the other factor. And between the factors, there would be a product. You can take a look at any of the examples we did. There are two factors in this case, and between them there's a product, and so on. So the problem with this particular stage here is, even though we didn't do anything wrong so far, it's just that going forward, or if you were to stop here, yes, there's a product between these two, but between the blue and the red, there's a plus or minus sign. So that expression that you have, it's not in factored form. So we haven't really answered this question. If only there were a way to go forward from here, and there isn't, unfortunately. So this would be an incorrect approach, grouping the first two. Okay, did anyone try grouping something else? You could try grouping, let's say, the first and the third. You could try it. Let's see what happens. I'll just mention no way forward from here. And I'll make a copy. And let's see if we can do this a little bit differently. I'll group the first one and the third one, second and last. So if I just rewrite this, I could say x squared plus 2x minus y squared plus 1. Is there some kind of factoring you could do here? Yes? No? Yeah, you could do some common factoring. You get x plus 2 inside. And what kind of factoring could you do here, if anything? -1. You mean you could take out -1? Okay. There's two things you could do here. One of them is to take out -1, and then what's left inside the bracket? -1. Okay. And again, nothing wrong has been done so far. But the thing is, when you do try to factor like this, when you factor by grouping in this manner, you're trying to aim to get the same bracket show up. And even in this case, because the first bracket is x plus 2 and the second one is something else, it looks like we're stuck. I know this one here could be factored even more into a difference of squares. You could try it. You could get y plus 1, y minus 1. And over here we have x times x plus 2 minus a 1. But even though this and that look factored, the entire expression is not. There's a minus sign between them. And that's, unfortunately, another dead end. We cannot try to factor anything more from here. Let me actually pose another question at this stage. How many terms do you count at this stage? So I'll just box it up. At this stage over here, how many terms do you count in the entire expression? You're right. If you say 2, you're right. This is one term, and this whole thing is a second term, right? And there's nothing common between those two terms. So again, this is a dead end. There's no way forward. So not the right way to do this. Now, if you've tried, let's say, the first two and the last two and didn't get far, if you try the first and the third, second and the last, and also didn't get far, then it's time to try maybe grouping 3 terms at a time. Let's try which 3 terms we could group. There is an x squared, there's a 2x, and there's a 1. Let's group those 3 together. You can rewrite this as x squared plus a 2x plus a 1. And there is, let's say, a minus y squared. Everything okay so far? Everyone okay so far? All right. Now, the thing about these 3 terms in blue, actually, let me write this in red so it contrasts better. In the 3 terms in blue, let's see if we can factor them in some way. Would common factoring work? between these three? Just these three. Anything in common? No, okay. But there are three terms, and do you notice how it's three terms means a trinomial, and the exponent here is a 2, the exponent here is a 1, so it's a quadratic trinomial. And we looked at how to factor quadratic trinomials last time around. So if I just do a little bit of this on the side, let's say I make a note here, and x squared plus 2x plus 1. Just as a way of recapping what we did last week, how many of you remember how to factor this out? So as long as you have three terms like this, and the exponent on, let's say, the leading term, the first term, is twice as big as the exponent on this one. Do you all agree the exponent on the x is 1? Right? So as long as the exponent here is twice of that, you could treat this as a quadratic trinomial. And what happens here is you're going to try to look for two numbers whose product is 1 and sum is 2. If you're wondering where that comes from, you can compare this quadratic trinomial with let me try a different color, with this one, ax squared plus bx plus c. And again, just for your own records, just identify a, b, and c. A would be the number in front of the x squared term, so it has to be a 1. B has to be the number in front of x, so it's a 2, and c is 1. And the reason why that's relevant is because the product would be a times c, and the sum would be b. So once again, we're looking for two numbers whose product, let me actually be more precise, two integers, which means they could be positive or negative whole numbers. No fractions, no decimals. So positive or negative whole numbers whose product is 1 and sum is 2. Can you think of two whole numbers that satisfy those two criteria? Zach, go for it. 1 and 1. Some of you might know how to factor this in a different way also, but because we haven't talked about it yet, I won't mention it yet. We will actually get to it today. But if you can factor it using trial and error. Think about the product. Product is 1 and it's positive, and the only two numbers that can multiply to 1 would be 1 and 1. So the two numbers you're looking for are 1 and 1. And 1. The other possible product would be -1 and -1. But I hope everyone can see why we can discount this one. We can reject this one, right? Because it doesn't add up to a positive 2. This one would add up to a -2. So this would be incorrect, and this one would be correct. When you, in the ideal scenario, you can go from here, think of these two numbers, very, very quickly. I'm just really, really trying to break this down. Any questions so far? No? Okay. Now, here's the other thing. If your quadratic trinomial has an a value of 1, so I'll just mention this over here. If a equals 1, then you can really, really quickly go into factored form directly. So there's going to be an x in both of these brackets, and the two numbers you thought of end up here. So I could write x plus a1 and x plus 1 again. And that's because both of my numbers were 1, positive 1. If any of them were negative, there would be negative signs here. Well, one of them. So long story short, the blue expression over here can be factored into x plus 1 times x plus 1. Is that okay so far? Any questions about that? No? Okay. What do you think we should do at this point to help us get to a factored form? Is it in factored form right now, the entire expression? No, because there's a minus sign here. So there are two terms. This whole thing is one term. This thing is a second term. And because there's an addition or subtraction between the two terms, We're not there yet. What thing do you propose that we could do to make our next step easier? What could I rewrite this blue expression as?
X plus 1 squared.
Yep, you're right. X plus 1 whole squared, like that. And we have minus a y squared. Now we're getting closer. Can anyone see something that this resembles? Can you see what this looks like? How many terms do you count again?
2.
2, and there's a subtraction between them. Difference of squares. And you can express each of those things as, each of those terms as a square of something. So, like the y squared is basically y squared. And the x plus 1 is already written as a square of something. So this whole thing is our a, this thing is our b, and a squared minus b squared has this factored form, a plus b times a minus b. So you could say, since that is true, our final answer would be, we'll have 2 brackets. A was x plus 1, so you could say a plus b would be x plus 1 plus a y, and b would be x plus 1 minus a y. Does that look like factored form? Yeah. We have, between these 2 brackets, there's a multiplication for sure. So that is the answer. It doesn't matter if you write this as x plus y plus 1, x minus y plus 1. Or if you were to interchange the brackets, they're fine. So one of the reasons this is a good example to look at is because usually with factoring you may have to use multiple techniques to get to factored form. And it could be in whatever order. Every situation could be different. Here we ended up using a little bit of quadratic factoring. And then we had to use, actually, sorry, let me start again. We had to use factoring by grouping. We had to group the right things together, first of all. Then we did a bit of quadratic factoring, and then we did difference of squares. 3 things. Before we go on to this section, I believe this is the second last section, we should really quickly take a look at one example I went over, I skipped over, I should say. It's this one here. So this is an example from section 8.3. And we're going to recap again factoring quadratic trinomials. I know we just encountered this, but let's do this one again. The thing about section 8.3 was, if you were to take a look at the previous examples in this section, the previous examples only had, or all had this common to them. The number in front of x squared was a 1. Even here, it's a 1. Even here, it's a 1. Except in this situation, it's a 2. Right? So we talked about how if the quadratic expression has a 1 at the front, like here and here, as soon as you think of the 2 numbers that satisfy the product and sum criteria, you can go into factored form. You could just jump directly into that. That's the main reason why you should look out for whether there is a 1 here or not. If you don't have a 1, like in this example over here, then you actually have to follow a slightly longer method. It's still very similar. You have to look for product and sum, etc., etc. But there's a slightly longer method involved. And we didn't talk about what happens if there's let's say a 2 or a 3 or a 4 yet. That's part of section 8.5. Now, if that idea is part of section 8.5, a good question to ask is, why is this example in 8.3? So what do you think we could do here? If I told you nothing else, and if I gave you this expression to try to factor, what would you try to do in terms of the things that we've already talked about? Miguel, go first.
You have to find the 2 numbers that multiply up to the negative 60, and 2 numbers that add up to
you're not wrong. You're not wrong at all. And in fact, you'll get the answer if you go ahead like that. But remember, the thing is, as soon as you think of your two numbers, you wouldn't be able to directly jump into this. You won't be able to. And the reason is there's a number that's not 1 over there, right? So is there something we can do to make a 1 show up over here? Stretching or answer? Answer also, okay. Kind of, not exactly. I won't say divide everything by 2, because is that an equation? You can factor 2. Yeah, so it's not an equation, so don't divide by 2. But you can factor. You're right. So we're applying a little bit of common factoring. There's 2 common to every single one of those. So you could take 2 out, and inside you're left with x squared plus 2x minus 15. So at least in this case, we can get rid of a number that's not 1 by doing some factoring. And now, if you take a look at the expression inside, could you really quickly try and factor this out using the whole product and sum idea? If you're not sure, let me know. I can help you out individually, but I'll leave this up for a bit. Please do try it. First of all, this is a trinomial, correct? It's a 3-term expression. And you also agree it's a quadratic trinomial? The main feature has to be that the exponent on this term is twice as big as the exponent on this term. So this could have been a 6 with an exponent of 3. You could still treat it as a quadratic expression. You could treat it as a quadratic trinomial. But anyway, let's come back to this idea. What I'd recommend doing is to identify A and B and C really, really quickly in this expression over here, underlined in red. So what's A here? 1, and B is 2, and C is negative 15. Perfect. And then, based on that, you can write this out. The product of the 2, let's say, mystery numbers we're looking for would be A times C, which in this case is 1 times negative 15, which is negative 15. And the sum of those 2 numbers would have to be the value of B, which is 2. Hey, question? Or oh, right, okay. Before you do, how many of you can think of those 2 numbers based on these criteria? Or would you still like some additional tips on how to find those numbers? You can find them? Well, someone said no. Okay, tips, okay. Hey, yeah. Negative 5 and no.
Oh, sorry, 5 and negative.
Yes. Yeah. So what I would recommend is focus on the product first, and use the sum very soon, but not initially. So think of 2 numbers that give you a negative product, and there's something to be observed here. If your product is negative and you're looking for 2 numbers, then it means one of those 2 numbers has to be negative. One of them, right? Next thing is to look at what gives you 15 when you multiply 2 numbers together. So one thing you can think of is 15 and 1. One of them could be negative, but it'll never give you a sum close to 2. 15 times negative 1 or negative 15 times 1 doesn't give you this. The next one you could try is 3 and 5. So make one of them negative. So you have 2 options. You could say 5 and negative 3 or negative 5 and 3. Both of them satisfy that criterion. But which of them would you reject based on this one? The second one, you're right. This one doesn't work because negative 5 plus 3 won't be a positive 2. But 5 plus a negative 3 is 2. Right? So based on that, you can say, well, this would be the correct pair of numbers. Is that part okay? And I know some of you can probably do all of this, the whole choosing of the numbers mentally, and that's actually even better. But if not, then you can lay this out in front of you. Next step would be, because our expression inside the bracket has an a value of 1, you can directly go into factored form for that expression. There's still a 2 outside. This 2 is from the previous factoring we did. And what would you put inside the bracket? How many of you are sure about what needs to go inside the bracket? Okay, so x, and what else is there?
Plus 5 and minus 3.
Yeah, and it doesn't matter where you put the plus 5, where you put the minus 3. You could put negative 3 here, plus 5 here, or you could put plus 5 here and negative 3 here. It's fine. So your final answer is this, but I'll just rewrite it. It's 2 times x plus 5 times x minus 3. That is the final answer. Since we just talked about factoring quadratic expressions where the a value is 1, and we talked about it at least twice because we encountered it just now twice, I think we are finally ready to talk about the general scenario. So we're still talking about quadratic trinomials, but in the general scenario, you could have a value of a that's not 1, like in this example. And can we do any common factoring here? Those of you who are in mechanical engineering, so the actual correct answer is yes, you can still factor something out, but what you'll end up having inside won't be whole numbers. You won't have whole numbers. You'll have fractions. But so for now, when I say can we do any common factoring, I should quantify it by saying can we do any common factoring that leaves us with whole numbers inside. And like in the previous example, we could take out 2, and we just had whole numbers inside. Would you agree that we cannot do that here? If I were to take out 2, we would get x squared plus, what would this second term become? 5 over 2. And this one will become 3 over 2. So we're trying to avoid getting fractions like this. And so for that reason, I won't recommend common factoring here. But again, we have 3 terms, and it's a quadratic expression. We have an exponent that's twice the exponent here. So let's think about what our a and b and c are, and think about the product and sum that we're looking for. Well, the product and sum that are related to the 2 numbers we're looking for. Let's say that's more accurate. A would be 2, B is 5, C is 3. Again, if you have any questions about how to identify A, B, and C, let me know. And does everyone remember what the product's going to be in this case? 6, yep, because it's A times C, and sum would be a 5, which is B. How many of you can think of the 2 numbers here? Don't tell me just yet, but as long as you can think about it, that is a good start. Would those 2 numbers be both positive, one positive, negative, both negative? Both positive. And we're saying they're both positive because of positive product and sum. They're both positive, you're right. So which 2 numbers?
2 and 3.
2 and 3, great. Makes sense, right? 2 and 3. Some of you, if you did think of -2 and -3, remember you can say no to this because it doesn't work with the sum. This would work with positive product but negative sum. But this is the one that works for positive product and positive sum. Okay, so now is the slight difference that we'll encounter. Since A is not 1, we would have to do this the long way. We would have to, let me mention what the actual process is called. We have to split the middle term. And by the middle term, I mean in the original expression, the 5x. And here's how we do it. We have 2x squared plus 5x plus 3 originally given to us. This is the middle term. And you can break this up using the two numbers we just thought of, the 2 and the 3. You can write this as 2x plus 3x, or you could write 3x plus 2x. It doesn't matter. But everything else is still the same. We have 2x squared plus here, and that over there. How many of you remember this method, by the way? Okay. This method, by the way, the splitting the middle term method, you can use in this method also when a is 1, except you don't need to because it's easier to just jump into factored form. But when a is not 1, and if you don't want to do trial and error, I would recommend this method because it'll give you the answer correctly without much ambiguity, let's say. So as soon as you split the middle term using those two numbers, here we have to do some factoring by grouping. So you can group the first two and group the last two. And what's the most you can pull out from each? Let's try common factoring. Anyone?
2x from the first.
Okay. 2x from the first, so we're left with x plus 2. And again, when you do common factoring, always check. 2x times x should give you the first term. 2x times 2 should give you the second term. Whoops, I made a mistake. Should be an x plus 1. There you go. Always good to do a check. And as soon as you're completely sure about this factoring over here, one thing we can use for the second part is we need the second bracket to be the same also. You can use that as a reminder. So keeping that in mind, what's the most you can pull out from here? One of you said it already. 3? Positive or negative? Positive 3. Okay, so if we use positive 3 as the common factor, what's left inside? X plus 1. And I'll just really quickly check again. 3 times x should be that. 3 times 1 should be that. Okay, we're good because we've verified both of these. And at this stage, how many terms do you count? 2. Yeah, this whole thing is one term. This whole thing is a second term. So that's one term, second term. And do you see what's common to both? Okay, and that common thing is what we pull out again. So the common, let's say, part in both of these is this whole thing. So if you pull that out, you could say x plus 1 in one bracket, and in the second bracket you could have 2x plus 3, whatever's left. So imagine if this wasn't there and this wasn't there. What's left is the 2x plus 3. And that would be the answer in this case. So here you can again begin by saying what A, B, and C are. And this allows us to figure out the product and the sum of the two numbers we're going to try to look for. First thing to notice is A is 3, B is negative 16, and C is negative 12. A would always be with the x squared term. B would always be with the x term. And then product would be A times C, sum is B. And these words here, product and sum, they're related to two whole numbers, positive or negative, that we have to look for. So product, sorry, I forgot to write this out. Product is A times C, which is negative 36. Sum is negative 16. And once again, if you look at the product, it's negative, which means one of those two numbers is negative. So after a few different tries, you can, or you should get these two numbers. 12, whoops. they'll come closest. And I hope, once again, everyone can discount one of them. Right, both of them work for negative 36. Or am I saying 3 again? Oops, times 2, and there you go. And you can always say no to this one in this case, because 18 plus a negative 2 will not give you a negative 16. Negative 18 plus 2 will give you negative 16. So, once again, since a is not equal to 1, we have to do this again, split the middle term. So if I were to rewrite the original question, 3x squared minus 16x minus 12. The middle term is this term over here, the negative 16x. And for anyone who wasn't sure what to do after finding the numbers, you would have to use those two numbers that you found to rewrite this into two terms. It doesn't matter which one of these you put first. You could say negative 18x plus a 2x or 2x minus 18x, up to you. But everything else is still the same. We still have a 3x squared here, and we have a minus 12 over here. Is that okay? You've got the answer, right, already? Okay. Once you split the middle term, you have to factor by grouping. Look for common factors between the first two and the last two. The most you can pull out from the first two is... Anyone? Derek, you want to try? 3 and 3x, great. So we can pull out 3x from here, and what's left inside is an x minus 6. Just always check really quickly. 3x times x should give you 3x squared, and 3x times the negative 6 should give you negative 18x. So that works. And what's the most you can pull out from here? 2. You're saying positive or negative? So if you think positive, to remember to actually write plus and then a 2. Right? That sign here is important, plus or minus. And let's see, if you take out positive 2 from each of them, you should be left with x minus 6. We can check 2 times x is that, 2 times negative 6 is that. All right, we've verified both of them. Hey.
I was going to say, if you ever don't get like both the same, like say it was x minus 6 and the other one is x plus 6, does that mean you messed up?
Yes, yeah.
Putting a negative or positive?
That's right, yeah. Which is why I would always recommend the first one that you do, be really, really sure about it being correct. Because then the second one should look like it. Now imagine if I, by mistake, pulled out a negative 2. And if I, let's say, still wrote x minus 6 inside, I would always recommend checking this one too. Would negative 2 times x give you that term? Because negative 2 times x would be a negative 2x, and this is a positive 2x. And negative 2 times negative 6 would have been a positive 12. So at least this way you can say, okay, this needs to be a positive 2. And that fixes it. But that's a good question to ask, yeah. If you don't get the same bracket, it means you've reached a dead end, or you're doing something wrong. One of those. With quadratic expressions like this, it would not mean that you've reached a dead end. It means you've done something wrong. And then what's common here would be this and this. So if you pull that out, you get x minus 6 as 1 bracket, and what's left inside would be the 3x plus 2. And that would be factored form in this example. So now we can talk about the final section within this chapter. It's on perfect square trinomials. And the thing about perfect square trinomials is we have sort of encountered this already in one of the examples, at least. But the aim of this section is not just factoring, but also how to expand using this idea. So there's two aims here. And that's what, let's say, the formula looks like for perfect squared identity trinomial. Sorry, I'll just rewrite it if you want. It's a plus b whole squared. You can immediately either expand into this, or if you had, let's say, a trinomial that looked like this, you could factor into that form really, really quickly by skipping a lot of steps. So a minus b squared would look like this, for instance. And they're just useful in terms of speed, let's say. You could speed things up in terms of factoring or in terms of multiplying expressions. So important thing to keep in mind, you could go both ways. You could be starting here, and maybe the question or the situation needs you to expand the expression. And then one way of expanding the expression would be to write this as a plus b times a plus b, FOIL it out, and eventually you'll get 3 terms. The other way, the quicker way, would be to recognize that a plus b squared is an example of a perfect squared trinomial, because when you expand it, you'll get these 3 terms. A and b could be anything. Similarly, with a minus b squared, you have this. So you could use it to expand these expressions to get that, or you can go from right to left. So you could start here or here and factor to go into that or that. You have those 2 main uses for this. I'll show you very soon where we could have used this already, where we've already encountered this. But for now, let's use this example here. Notice how the first thing you should notice is we're not being asked to factor anymore. We're being asked to square the following expression. Okay, so factoring is not what's being asked here. So we have an expression like this, and we're trying to figure out what is 2x plus 3 squared going to look like. That's the question. Once again, you could FOIL this out. You could say this is the same as 2x plus 3 multiplied by 2x plus 3. And you could open up the brackets like that. But the aim of this section is to show you how to use that particular formula. Right? So for now, let's move away from that for a second. Let's compare this with a plus b squared all you really need to do is identify a and b in this expression. And then you can use that. Everyone can see a and b? Yes, a would be this whole thing, 2x, and b would be just the 3. So what this expansion is really saying is you'll have to square your a, you'll have to square your b, and in the middle you'll have the 2ab is the product of ab but doubled. So you'll have twice of the product of whatever a and b are in your situation. Once again, a was 2x, so 2x needs to go here. I'll move this down. B was 3, so 3 needs to go here. And in the middle, both 2x and 3 get substituted here. That's us using this right side of the formula, let's say. I'll just make up another example if you would like to try it out more. But once you do the substitutions correctly, just evaluate a little bit more or simplify a little bit more. What is 2x whole squared going to become? 4x squared, yep. I'll do the last term next. So 3 squared is a 9, positive 9, so I'll put a plus sign here. And here, it's 2x times 3 and then doubled. So 2x times 3 is 6x, 6x doubled is 12x. So you could say 2x plus 3 whole squared is really just that when you expand it. Does that make sense? Couple of common mistakes I've noticed. Well, not a couple, just one really. Something I've noticed in the past, and I should just make a note here. Just keep it in mind, this is not the same as that. I've just seen it happen, so I have to mention it. And you can prove that this is not the case because 2x squared plus, 2x plus 3 squared is definitely 2x plus 3 times this. The red one is true. That one is not true. And you can manually multiply by foiling this out. And you can verify that the answer will never be that simple. These two do show up. 2x squared is 4x squared. 3 squared is 9. Those two things do show up in the answer, but there's a third, let's say, component. Is that okay so far? Any questions? All right, in that case, let me just make up a couple of questions here. Let me go here first. And see if you can pay attention to the actual question or instruction in the question. So here's one example. Here's another example. In the first example, let's say I ask you to square or expand expression over there. And in the blue situation, let's say the question is to factor. Small correction, there should have been a square on the bracket, and that's because I didn't use the word square over there first. The formulas we just talked about, the a plus b squared equals a squared plus 2ab plus b squared, or a minus b squared. You can use these formulas to factor expressions if you have a few things going on. Like in the expression here, we have 3 terms. That's a good sign because on the right side there are 3 terms. But the second quick visual check that you should do to see if you can even apply these formulas is take a look at the middle term. And in the middle term, this number that you see here, or this entire term, the 84xy, is that 2 times the product of A and B? And I guess really to answer that question, you'd have to do a few quick adjustments. How many of you can see what A needs to be here and what B needs to be from here? In other words, is there a way to write the first term as a square of something? You said 6, and does that work as the first one? And the last one you could say is 7y squared. Right? As long as you can kind of really quickly imagine this either in your mind or you can even write this down on paper, as long as you can express the first and the last term as perfect squares. That's one thing you have to be able to do before you can apply this. The second thing you have to do is, if you do this, here is your you're saying that this expression is A and this is B. Is that middle term twice of the product of A and B? So when you multiply A and B together, you get 6 times 7, which is 42, x times y, which is xy. So 42xy. Is 84xy twice as big? Yes? If the answer is yes, then you can use one of these to factor. So twice of AB. And the correct one to use would be the first one because we have only positive signs. So you can discount using this one. I'll remove that for now. And since we've already identified A and B, and as long as you notice there's a plus sign in front of the middle term, the only thing you have to do is have a square outside a bracket and write in your A, which is 6x, B, which is 7y, and a plus sign shows up between them. That's it. That's a quick way of factoring this expression using that formula, let's say. There is another way of doing this which would take a lot longer. But again, where possible, these formulas help to just shorten the amount of time and effort that's needed. Is that okay for that question? And you can always check 6x plus 7y whole squared. If you reuse the formula, you should get that expression. 6x squared should give you the first term. 7y squared should give you that term. And the middle term would be 6x times 7y multiplied by 2. So 84xy. In the other example, as long as you're able to keep in mind what A and B are, you can use the correct formula. You're starting on the left side, you need to get to the answer on the right side. So as long as you identify A and B, use, in place of A squared, put in your A. Or let me do it this way so it's a little bit more clear. So 5y minus 8 squared is going to be something squared minus 2 times these something in there as well, and then something else squared. Right, and again, it's just a matter of identifying A and B from the original expression and putting A here, B here, B here. That's a quick way of doing it using just the formula here. A is 5, 5y. So 5y goes here. B is 8, so it goes here and here. And the final step would be to just simplify this a little bit more. 5y squared becomes 25y squared. 8 squared would be 64, and twice of 5y times 8. No, it won't be minus 8. You can again verify this by using FOIL also. You'll and you can kind of see it this way. Let me ask you really quickly, since you asked the question: 5y minus 8 times 5y minus 8. If you just do the last multiplication, the negative 8 times the negative 8 becomes a positive 64. And that's where this guy is coming from. The middle term will have a negative sign, and it'll be 81.